Hello, my name is Dr Alex Pulis. I'm a lecturer of organic chemistry in the School of Chemistry here at the University of Leicester. It's a great pleasure to be able to tell you about some of my research today, which is concerned with discovering new methods for chemical synthesis. Now, chemical synthesis is a wide-ranging topic and it's central to science. It can be broadly defined as the purposeful execution of chemical reactions to obtain a product. We can also think about chemical synthesis as the way we build molecules from other molecular building blocks. Chemical synthesis is very important as the results are all around us. For example, plants produce the oxygen we breathe via chemical synthesis. When performed by us, chemical synthesis can provide medicines that treat our loved ones. It also helps us understand biology, it helps to feed us, and provide materials for everyday objects. Given the universal application and scale of chemical synthesis, it is important to develop new methods of chemical synthesis that are sustainable and more efficient. As with making anything, whether it be a toy, a house, or baking a cake, the materials that we start with and how we put them together is very important. And these aspects of chemical synthesis are the main themes of my research here in Leicester. In my research group, we are finding new building blocks to use for chemical synthesis. That, for example, come from renewable and readily available sources. And we discover new ways to put them together in the most efficient way possible, by developing new reagents and new catalysts. These are essentially the glue that sticks these molecules together by allowing new bonds to form. The first project I would like to tell you about is a collaborative project between Peakdale Molecular, who are now called Concept Life Sciences, and us. In this project, Peakdale were very interested in making molecules like these, ones that have a ring-like structure to them that is attached to some other group. Here this group might be a carbonyl group, an alkene, or another ring. Now this type of motif or substructure is very important as it is found in several medicines. For example, those that treat HIV, diabetes and heart diseases, and one used for controlling pain and in organ transplants. In fact, in many, many more. So, as a company, Peakdale were very interested in making compounds like these because they are involved in the discovery of new medicines. And they wanted to be able to make this type of structure very efficiently. So we came up with a reaction that uses two readily available building blocks, an aryl halide and an alkyl chloride. We had to convert the aryl halide into an aryl boronic ester to allow it to react with the alkyl chloride. We did this by using an efficient diborane reagent and a catalyst. The catalyst essentially allows the diborane to stick to the aryl halide to form the aryl boronic ester. Now, one of the advantages of this process was that the catalyst that we used to stick the diborane and the aryl halide together is also used to stick the aryl boronic ester and the alkyl chloride. This meant that the whole process could be done in one reaction flask. This is what we call a one-pot reaction. And one-pot reactions save waste. If you consider when you're cooking, the fewer pots and pans you use mean the less washing up you have to do afterwards. Therefore, this saves waste. More recently, our research has been involved in discovering new catalysts, so new ways of gluing molecular building blocks together. Now, several reactions use precious metal catalysts to do this. Now, these precious metals, they're very versatile and allow a fantastic array of different reactions to take place, but they do have some drawbacks. Some are very expensive and have unpredictable prices. This is a problem if you're doing a large-scale chemical synthesis and are trying to keep to a budget, especially if the price of one of your key components keeps changing. Their use also involves a significant environmental impact as they are obtained from mining. They are generally toxic and have strict limits on the traces allowed in products meant for human consumption. They have poor substitution and recycling rates and are considered high supply risk because over 99% of these metals are imported into the EU. Our research is addressing this by exploring the reactivity of readily available main group elements to replace these catalysts. In particular, we're looking at my favourite element, boron. One area we are very interested in is in chemical synthesis via the functionalisation of carbon-hydrogen bonds. This is potentially a very efficient way to build molecules, as only one H atom is wasted in making the new bond. However, precious metals are often required to make this happen. We have developed a reaction that uses boron-based catalyst to functionalize carbon-hydrogen bonds. Here, the boron catalyst activates a molecule that contains a CH bond for a reaction with another molecule. The products that we are making via this method are related to medicines and will enable those who are involved in the discovery of new medicines to efficiently make the molecules they need. I have a big thank you to say to my very talented and hard-working team. Without them, none of my research would be possible. So Anna is a PhD student in my group. She's from Spain. Laura is also a PhD student, and she graduated from the University of Leicester last year with an M.Chem degree. Tom and Amy have just recently completed their final year M.Chem research projects in the group, and Javid is a master's student from the University of Hamburg. I would also like to thank the University of Leicester and the Royal Society for supporting this research, and thank you for listening.